In the vastness of space, we're all hurtling through the cosmos at unimaginable speeds.
But why can't we feel it? That's what I've been researching.
Dr. Emma Blackburn, astrophysicist, had stumbled upon a revelation.
Imagine you're on a train moving at a constant speed. You can walk around as if you're stationary.
But we're moving much faster than a train in space.
Exactly. Now picture this. Here's Earth, spinning, orbiting the sun, moving through the galaxy. We don't feel the speed because there's no acceleration relative to our surroundings.
So it's all about relativity.
Precisely. Einstein would be proud.
As understanding dawned, Dr. Blackburn revealed a truth that would reshape their view of the universe forever.
Right now, you are spinning along with Earth, orbiting the sun, hurtling around the Milky Way's center, and even moving relative to distant galaxies. Summed together, these motions amount to speeds of millions of miles per hour. Yet, you stand here feeling utterly still. This apparent paradox arises because our senses evolved for survival on Earth's surface, where steady, uniform motion is indistinguishable from rest. In physics terms, feeling motion requires a non-uniform movement, an acceleration or a change in direction. Since cosmic motions unfold smoothly and steadily, without abrupt changes in velocity, our bodies fail to register the immense speed. The paradox is resolved once we understand that perception depends not on absolute speed, but on changes in that speed. Example: consider Earth's rotation at mid-latitudes, 700 to 1,000 miles per hour, and its orbital velocity, 66,000 miles per hour around the Sun. Add the Sun's orbital speed around the Milky Way, 514,000 miles per hour, and the galaxy's motion relative to cosmic landmarks, 1,300,000 per hour. Despite these huge numbers, you feel stationary because every part of your environment shares these motions. Analogy: imagine sitting in a smoothly moving train with the blinds closed. Without looking outside, you can't tell if you're racing along at 80 miles per hour or standing still at a station. Everything inside moves with you, providing no hint of the train's true speed. Inertia, described by Newton's first law, states that an object in uniform motion will continue moving at the same speed and direction unless an external force acts upon it. Earth's rotation and orbital motions are stable and nearly constant over human timescales. Because there is no abrupt acceleration, no jerky stop-and-go effect, your inner ear and sensory receptors that detect changes in motion remain quiet. Essentially, you, the atmosphere, and the ground beneath you are all coasting through space together at constant velocities. In this inertial frame, being stationary and moving uniformly feel identical. You experience no internal cue that you're traveling at breakneck speeds. Example: when an airplane reaches cruising altitude and speed, passengers can walk around, pour drinks, and read comfortably. Even though the plane moves hundreds of mph per hour, the ride feels tranquil because its speed stabilizes and no significant changes in motion occur. Analogy: think of drifting downstream in a quiet river. If the current flows evenly, you feel no sense of rushing movement. Your boat, the water, and you all share the same steady motion, leaving no clue that you're covering distance at a good clip. Speed is always measured relative to something else. On Earth, we typically gauge motion by comparing ourselves to a stationary object like the ground. In space, no absolute rest frame exists. Our planet orbits the Sun, and the Sun orbits the galactic center, but the galaxy itself moves relative to distant quasars and the cosmic microwave background. Each reference frame can claim itself at rest and others in motion. Without a universal stationary backdrop, the idea of feeling cosmic motion is moot. We pick Earth's surface as our frame of reference, and since we move along with it, we feel no motion. Example: inside a car, you appear motionless relative to the seat and dashboard, but zooming past roadside trees reveals your true motion. In space, there are no handy trees at rest to give away our speed. Analogy: picture two boats drifting side by side at the same speed. From each boat's perspective, the other seems motionless. Without the distant shoreline, neither crew would guess they're moving at all. Cosmic motions occur over staggering distances and timescales. Earth takes 1 year to complete its orbit around the Sun, and our solar system takes roughly 200 million years to circle the Milky Way's center. Changes in direction or speed are spread out so thinly over time that any acceleration is imperceptibly small. Human senses are keenly tuned to immediate changes, falling, stopping, turning sharply, not to gradual shifts extending over months, years, or millennia. In cosmic terms, we're on a ride so smooth and so slow-changing that we might as well be motionless. Example: if you accelerate a car from 0 to 60 miles per hour in 10 seconds, you feel a clear push backward. But spread that acceleration over an entire year, and you'd never notice you were speeding up. It would be too subtle. Analogy: imagine watching paint dry on a massive wall. The drying process is happening, but at such a slow pace that at any given moment, you see no change. Cosmic accelerations are like that, real but too gradual to perceive. Gravity pulls us toward Earth's center with a force far stronger than any subtle outward or sideways pull from our planet's rotation or orbital motion. This gravitational anchor ensures we remain firmly on the ground. The slight centrifugal effect due to Earth's spin reduces your weight by a tiny fraction at the equator, but it's negligible. Since your sense of balance and orientation rely heavily on feeling weight and pressure, and these remain constant, there is no signal that you're flying through space. Essentially, gravity sets the baseline that masks any small inertial clues we might otherwise detect. Example: at the equator, you weigh slightly less than at the poles, but this difference is minuscule, on the order of a fraction of a percent. This tiny variation can't convey the sensation of rapid rotation. Analogy: picture yourself strapped into a gently rotating playground carousel that's moving so slowly you barely notice. The strap, gravity, keeps you secure, and since the rotation is steady, your body doesn't interpret this as motion. Einstein's theory of relativity teaches us that all motion is relative. There's no absolute right way to say who is moving and who is still. From your viewpoint, you can consider yourself at rest and the universe rushing past you. Both perspectives are equally valid. This principle means that feeling cosmic speed is a matter of perspective, since we define our rest frame as Earth's surface, and that frame moves uniformly with us. No internal experiment can reveal that we're moving through space at extraordinary speeds. Example: if you're in a spaceship cruising smoothly in deep space, you can say you're at rest and everything else is moving. Without external cues, your claim is as good as anyone else's. Analogy: think of two people on parallel moving walkways. Each sees themselves as stationary while watching the other glide away. Without a fixed floor or reference point, it's impossible to determine who's really moving. Calling it a paradox highlights the gap between human intuition and physical reality. Intuition suggests that traveling at millions of miles per hour should feel dramatically different than standing still. However, physics shows that constant velocity is indistinguishable from rest. The paradox dissolves as soon as we realize that speed itself is not what's felt, only changes in speed, acceleration, or direction. Since cosmic motions are steady and unchanging on human timescales, we experience no sensation of speed. Astronauts aboard the International Space Station orbit Earth at about 17,500 miles per hour, yet they feel weightless and still because they share the station's frame and velocity. No sudden forces inform their bodies of high speed. Imagine holding a spinning coin between your fingers. If you spin it gently and steadily, it feels smooth. Increase the spin suddenly, and you feel a jolt. Without that jolt, steady motion is as good as no motion. Consider astronauts in low Earth orbit. They're moving at tremendous speed around the planet, but they don't feel it. Instead, they experience microgravity because they're continuously falling around Earth, matching Earth's curvature. Inside the spacecraft, everything moves together, creating an environment where relative motion between objects is minimal. This scenario is a miniature version of our life on Earth. Shared motion prevents any sensation of speed. Observing the planet outside the window reveals motion, but inside, it's business as usual. Example: astronauts can float effortlessly in the ISS. If they tried to guess their speed without looking outside, they'd have no clue they were zooming around Earth every 90 minutes. Analogy: if you and a friend jump off a tall diving platform together at the same speed, you'll both be in free fall. Relative to each other, you seem still, even though you're both plummeting toward the water. Understanding why we don't feel our cosmic speed enriches our view of the universe. It reminds us that our perceptions are limited to local experiences of acceleration, gravity, and motion. The laws of physics operate on vast scales, where uniform motion is the norm and absolute rest doesn't exist. By recognizing this, we appreciate that feeling still is simply a matter of sharing a smooth cosmic ride with our immediate environment. Rather than a paradox, it's a profound insight into the nature of motion, frames of reference, and the elegant consistency of physical laws. Example: from Earth's surface, the stars appear to slowly wheel overhead each night, but this stately dance conceals mind-boggling speeds. We never feel these speeds because everything around us participates in the same grand movements. Analogy: our place in the cosmos is like sitting quietly on a majestic, smoothly gliding ship. The ship sails immense cosmic seas, but the deck beneath our feet feels as solid and still as a quiet porch, no matter how fast we're traveling.